Let's do a little bit of volume stuff because some people were asking about volume. Let's say, sure, let's try this one. We want to find volume. Let's see, I myself some notes here. One second. Where did I put my notes? Everywhere is where I put them to be. There we go. Sure. Of regions bounded by y equal to x times the square root of, yeah, I like that, sine of x. And y equals 0. Revolve. Sorry, I'm not speaking very loudly. Find the volume of the region bounded by y equal to x times the square root of sine of x and y equals 0 in quadrant 1. Just the first period, because this would go on forever technically. Revolved around the x-axis. And truthfully, I don't really know what this function looks like. Like, I have an okay-ish idea. I'm still going to graph something. So I'm looking at quadrant 1. So I know I don't need to worry about the left side or the bottom, really. And square root of sine of x, I don't really know. But I know that sine is positive from x equals 0 to x equals pi, because that's your first sorry. So there's two different quadrants here, right? I'm talking about the unit circle for a second. When sine goes from 0 to pi over 2, or when the angle goes from 0 to pi over 2, sine is positive. And when the angle goes from pi over 2 to pi, sine is still positive. And I know that sine of 0 is 0, and sine of pi is 0. So I'm looking at something that's going to go from 0 to pi. And I don't exactly know what it looks like, but it might look something like this. And I probably didn't do the best job describing this region, because I should have been like, I only want the first section of it, because technically after you go from pi to 2 pi, this would kind of repeat and you get more sections, but we only want the first one. So we're taking this region. And I could have found those limits of integration by setting x squared sine x equal to 0, but I was just trying to think about where I knew it was equal to 0. And then we're going to revolve it around the x-axis. And I know it's been a little while since we've done one of these, so I'll remind you, what we're doing is we're taking a little strip, a little rectangle, and we're thinking about revolving that rectangle around the axis. And when we do that, we get a disk. In this case, sometimes we get a washer. In this case, we're getting a disk. And the volume of our disk is just the area of the circle, pi times whatever our radius is squared, times the thickness of the disk, which is a small change in x. And here our radius, almost always our radius is just how far we are from the axis of rotation, which is typically just the function. So in this case, the volume of our disk is pi times x times the square root of sine of x squared dx. Sorry, I said one thing. Let me clarify. The radius is just x times the square root of sine of x, and then the volume of the disk is pi times that radius squared times dx. Of course, yes. Is that better? Yeah. Good. Sorry about that. And yeah, maybe I shouldn't use this. This green pen doesn't show up super well, so I will not use your green pen. Sorry. Retired. Okay. So the only other thing left to do is then, well, not the only thing. The next thing to do is then to actually say, well, we don't just want the volume of that one disk. We want the total volume. So the total volume is going to be the integral from as far left as 0 to as far right as pi of pi times x times the square root sine of x squared dx. Let's make this simple. So we set up our integral. Great setup. And sometimes, and I should make a real strong point of this, sometimes on an exam, they will just ask you to set up a volume and not find the actual volume. So make sure when you take an exam, if you have, I know some of you just took an exam, but if you're taking an exam and volumes are on there, make sure you read the question very carefully and distinguish between whether or not you're being asked to just set up the volume or to set up and then evaluate. Typically, if you're asked to just set up, it'll be in big bold letters. Just set up, don't do anymore, but don't do more work than you need to. But here we're being asked to find the whole thing. So let's do it. So if I simplify this, I'm going to bring this pi out in front. And then you have a quantity squared, each factor gets squared. So I'm going to have x squared, and the square root of sine of x squared is just sine of x. And now you might notice we're in an integration by parts sort of situation. It's definitely not a u sub. There's no good choice for u here, whose derivative is also there. And it definitely does look like a mixture of things. I have x to a power, or an algebraic term. I have a trig term. So let's go ahead and move on down here. Now, here's something I want to say about definite integrals when you're doing integration by parts. Really not fun to carry those limits of integration throughout the whole entire problem. Let me show you what I mean. We're gonna do it this way. Not really. Yeah. We're gonna do it the somewhat nicer way. So we're just gonna instead, we will start with or look at just the indefinite integral of x squared times sine of x. And then we'll adjust at the end. And I really, whenever I have a definite integral and the process is more complicated than just like anti-differentiating it and knowing what it is, like you have to do a u sub or something else, I often just like to do the indefinite integral first and then at the end kind of go back and then do the definite part. So let's do this. Okay, so we're going to let u equal x squared. dv is going to be the rest. Our du is 2x. Our v is the antiderivative of sine of x, which is negative cosine of x. I did forget the dx up here. dv is the entire rest, so dv is sine of x dx. So then this integral is going to be equal to u times v, so x squared times negative cosine of x, minus the integral of v du. Oh gosh, I'm forgetting dx is everywhere. My du should have been 2x times dx. v du is minus cosine of x times 2x dx. Doing a little bit of rewriting, this is equal to negative x squared times cosine of x. Minus minus is plus. I would also pull out the constant 2 there. And then I have the integral of x times cosine of x. There's no good reason for putting the x first other than it just feels right. Like I would never write cosine of x times x. I would always write x times cosine of x. Question. I'm ignoring the pi. Your good question. That you're right. I'm just focused on this right now. At the end, I'll throw back in the constant multiple and the limits of integration. But excellent question. Yeah. And then I'll point out that here we're once again in an integration by parts situation. I have an algebraic term or an any power of x term times a trig term. I'm going to do integration by parts again. So, and I'm going to use a different color here. So for this integral here, integration by parts. So now we're going to let u equal x. dv is going to be the rest, which is cosine of x times dx. Our du is going to be 1 times dx. And our v is the antiderivative of cosine, which is sine of x. So watch for a second here. We're going to get that this is equal to still this first term, negative x squared cosine of x, plus 2 times the entire integration by parts here. So that's going to be u times v, x times sine of x, minus the integral of v du, sine of x dx. The point of this process was to make that integral simple enough that we could actually just anti-differentiate it. And now we have, because we know what the antiderivative of sine is. It's negative cosine. So rewriting this, yeah, let's do this in 2 steps. We're going to get negative x squared times cosine of x plus 2 times the entire quantity, x times sine of x minus negative cosine is plus cosine of x. I don't need to write a plus c here because this is just my own side work that I'm doing for the purposes of a definite integral. So I don't need the plus c. I could write plus c, it wouldn't be wrong, but it's not necessary here. And then I would like to distribute this too. The one thing I want you all to see is that bringing this 2 out in front here means that after you integrate this and get these 2 or more pieces, you do have to distribute that to each of those terms. So we're going to get negative x squared cosine of x plus 2x times sine of x plus 2 cosine of x. Great. So now what I'm going to do is I'm going to go back and say, well, I know that the antiderivative of x squared sine of x is this long thing here. So now if I want to find the definite integral of x squared sine of x from 0 to pi times pi, I'm just going to do that by using the fundamental theorem of calculus, really is what I should say. I'm going to take the antiderivative, which I just found, and plug in my limits of integration. So I'm going to get the constant pi times the antiderivative of x squared sine of x, which is all this, negative x squared cosine of x plus 2x times sine of x plus 2 cosine of x, evaluated from 0 to pi. And then we plug in like we usually would for a definite integral. And I'm going to try and not use up all the paper here. So I'll remind everybody that sine of 0 is 0, cosine of 0 is 1, sine of pi is 0, cosine of pi is negative 1. Right? 0 over here where cosine is 0, cosine is 1, sine is 0, pi over here where cosine is negative 1 and sine is 0. So plugging in, I'm getting negative pi squared times cosine of pi, which is negative 1, plus, I don't really even want to write anything, so I'm going to get 2 times pi times sine of pi, which is 0, plus 2 times cosine of pi, which is negative 1, minus, now we plug in 0, and you get 0 times it doesn't matter, plus 0 times it doesn't matter, plus 2 times cosine of 0, which is 2 times 1. And then simplifying here, we get negative pi squared times negative 1 is positive pi squared, plus 0, minus 2, minus 2, minus 4. I do a quick check to be sure that that's a positive number. It is a positive number, so great. We feel good about our answer. So I would always recommend if you see that your integration process is going to be for a definite integral, is going to be kind of complicated, I would really, really recommend doing the indefinite integral first, doing all that work, not having to carry the 0 and pi with you. Right? So I'll just point out, if I was going to do it the other way, here's what I would have had to write from 0 to pi, and then here it's evaluated from 0 to pi, from 0 to pi, right? I don't want to write all that every time. It's really terrible. But you could. It just feels real silly. And then at the very end, I do like that. Right, it's unnecessary. It's more bookkeeping than I want you to do, than you want to do. Questions about this before I say one more thing about it? I will also point out that this integral would have been a prime candidate for doing tabular integration. So instead of doing integration by parts twice the long way, we could have instead said that, oh, for the integral of x squared times sine of x, right, this is one of the 3 types of integrals that lend themselves to tabular. We could have been like, all right, well, u is going to be x squared, and then take all the derivatives of x squared until you get down to 0. And then our dv is sine of x. And we take all the antiderivatives until we've done the same number of entries. So the antiderivative of sine is negative cosine of x. The antiderivative of negative cosine is negative sine of x. And the antiderivative of negative sine is positive cosine of x. And then it's going to be plus the product of those things minus the product of those things plus the product of those things. So our integral here would have been plus x squared times negative cosine of x minus 2x times negative sine of x plus 2 times cosine of x, or more succinctly written, negative x squared times cosine of x plus 2x times sine of x plus 2 times cosine of x. Which I'll remind you is exactly the same thing we got when we did it the other way. If we look back here for a second, our integral was negative x squared times cosine plus 2x times sine plus 2 times cosine. So there's a nice demonstration of the fact that the tabular method really does work. You're just doing a shortcut. And really what's happening here, so check it out for 1 second, right? So I'll just point out that in your first iteration, I'm going to try and use some different colors here. There's your U, and there's the V associated with it. So when you do this, you get U times V. And then we do minus the integral of V du. So we're doing the integral of 2x times cosine. Okay, this is where I'm simplifying is probably not my friend. Right, this next right here is going to be minus the integral of 2x times negative cosine x. So then we have to do another u and a v there. So for this new one, there's our u, 2x, and there's our dv, and there's our v. So you get another u times v. I'm use green for a second. I know I said it's retiring it, but I'm going to use it anyway. There's my u, there's the associated v. Finally, over here, we get 2 times cosine. That's going to be another, I don't love that there. That's really where you're just getting the integral of the last thing. So like it's the integral of your last, yeah, this is your last v. I guess no, that's still your, sure, you can see that's, sorry, I'm having trouble like justifying exactly why I'm saying this in my head. Sure, that's, you can say that's anyway, I guess. So that's kind of how this is working. Like every step, you're just getting the next u and v and multiplying them together. And in this type of example, you're going to run out of u's eventually because the derivative of u, if you keep taking it, is eventually 0. I can't stress enough. This only works. This tabular integration only works for 3 types of integrals. I'll say them again, just because I know I've said them before, but I'm saying again. Only works for something like the integral of x to the n times sine of x, or x to the n times cosine of x, or x to the n times e to the x. You can be a little more loose with that. It doesn't have to be just the power of x. It could just be some polynomial. Like actually right here, if you really wanted to make life even more challenging, you could say that something like x cubed plus 2x plus 1. That would technically work as well. It just has to be something that if you take enough derivatives of it, the derivatives will eventually be 0. And then the dv thing has to be something whose antiderivatives are essentially cyclical, that never get more complicated when you start anti-differentiating again and again and again and again. Yeah. And the only functions we know that really fall into that category are sine, cosine, and e to the x. Cool. Let's do another one. Not get out of order. Yeah, let's see. Sorry, let's do one more of those. Yeah, did we do that one yet? Sorry, I tried to remember all the things we've done. Let's look at, sure, I have another example here in my head. Yeah, sure. All right, let's say we want to find the volume of the region bounded by f of x equal to x e to the x, y equals 0, and x equals 1 around, again, the x-axis. By revolving, sorry, I forgot the important, but revolving, and the volume of the region bounded by revolved around, sorry. Writing the words for these is always not fun. I know what I want to say in my head, but making it come out in words sometimes is challenging. Find the volume of the region bounded by these three things revolved around the x-axis. There's probably a better way of saying that, but this is what you get. As is typical with these problems, we have to draw the region. We don't have to draw it perfectly. We just have to have some idea of what it looks like. F of x equal to x e to the x. I don't know exactly what it looks like, but I know it's vaguely. Yeah, I don't really know. Actually, it's going to be something like this. Probably looks something like that. Negative to the left because it crosses the x-axis at the origin. It's positive to the right. And then my bounds are going to be this function, y equals 0, or the x-axis, and x equals 1. So I'm looking at something like this. It's good to draw the strip every time, I think, but at some stage, I think we can move past that. But here, if I'm drawing my strip, there's my strip. The radius is clearly just the function. So our volume here is going to be the integral of pi times our radius squared dx from 0 to 1. Then we do the usual kind of thing. So we're going to rewrite it. I'm almost always, probably always, going to bring that pi out in front as a constant multiple. And then we have the integral from 0 to 1. You're squaring each factor, x squared times e to the x squared. Well, let's make it less terrible. E to the x squared is just e to the x times e to the x, which is e to the 2x. Or you can multiply the powers if you want to see it that way. This is pi integral from 0 to 1 of x squared e to the 2x dx. Once again, we find ourselves in a situation where we have to use a more complicated method of integration with a definite integral. So over on the side here, I'm going to do the integration by parts. And I'm going to do it tabularly because I can. Right? This is another one that meets the condition. Oh, I could have made it more fun. I could have made it more complicated. That was interesting. So here, so I want you all to do the integration by parts. So off on the side, I want you all to start with a u of x squared, a dv of e to the 2x. Find all the derivatives until you get to 0. Find all the antiderivatives until you've done as the same number. Your antiderivative should divide by 2 every time. And then after that, plus minus, whatever. And after you've done, so if you've done those things, then find your integral by doing. I'll write it by doing that times that. Whatever you have there. We should ask you all questions for this. Let's see. So making my u column here, the derivative of x squared is 2x. Derivative of 2x is 2. Derivative of 2 is 0. For my Antiderivatives, the antiderivative of e to the 2x is e to the 2x divided by 2. The antiderivative of that's going to be e to the 2x divided by another 2. So it's going to be e to the 2x divided by 2 times 2. And finally, the third one down here is going to be e to the 2x divided by 2 times 2 times 2. Whenever you would take a derivative and multiply by a constant, your antiderivative is going to make you divide by that constant. Again, these are examples of what I like to call mini u substitutions. If you were going to find the integral of e to the 2x, you could let u equal 2x and then do it that way, but we didn't. We just did it faster. So then the integral of x squared e to the 2x dx is equal to x squared times e to the 2x over 2 minus 2x times e to the 2x over 4 plus 2 times e to the 2x over 8. So then to find this, I'm going to take that antiderivative and just toss it into my formula here. So I'm going to get I times the antiderivative of x squared e to the 2x, which is exactly that. Let's do a little bit of simplification here. Yeah, there's a lot of simplification we could do to make our lives easier if we really want to. Well, let's not do all that. 1/2 x squared e to the 2x. 2 times 1/4 is 1/2 x e to the 2x, and 2/8 is 1/4 e to the 2x. From 0 to 1. And then we plug in the 1, and we get pi times 1/2 times 1 squared times e squared plus 1/2 times 1 times e squared plus 1/4 times e squared minus, and then we plug in 0, and we get 0 plus 0 plus 1/4 times e to the 0, which is 1. And then you probably could simplify that more if you felt compelled to. We're going to get pi times 1/2 e squared plus 1/2 e squared plus 1/4 e squared is 5/4 e squared, right? 2/4 plus 2/4 plus 1/4 is 5/4. So 5/4 e squared minus 1/4. Kind of a gross final answer, but I should ask you all, have you talked in class, in either class, about revolving around axes other than the x-axis? Like, have you revolved around lines like y equals 2 or x equals 3? Nothing like that? Not even the y-axis? Cool. Good. I mean, not necessarily good, but not something we have to worry about. So if I'll ask, if that does come up, like if your teacher does ask something or assigns a homework or problem where you're revolving around anything other than the x-axis, let me know. We can certainly talk about it. Okay. Sure. Okay, yeah. Anyone start talking about partial fractions yet? I didn't think so, but it's not okay. So good. So great. Talk more about integration by parts. We'll do some trig u substitution problems because people were definitely asking about that. And oh yeah, all right, let's do this example. Integral of natural log of x over x to the third. For some reason, natural log ones tend to feel more confusing, even though they're not really that much more confusing. Yeah, of course. Yeah. What's up?
Not the very last line, the one above it.
Right here?
Yes. Is that a plus?
It is. I made a mistake. Thank you so much. I didn't catch that until just now. No, sorry. I know I moved kind of fast. It makes it hard to kind of say, hey, James, but that should definitely be a minus sign. Good catch. That's really a minus there, which means we really, the 1/2 e squared and the 1/2 e squared should cancel each other out. And we should really just have a pi times 1/4 e squared minus 1/4. So that should really be a 1, not a 5/4. So that's a 1/4. So really, if we wanted to, we could write our answer very nicely as pi times e squared minus 1/4. Good catch. Thank you again. Let's say you made that mistake on an exam. It'd probably be not the worst thing in the world, right? Because you've shown all your work, you've shown you've shown you know what you're doing. Probably missing a point, half a point at the most there, because it's a small error in the bigger context of doing everything else right. That said, we should still try to avoid them. All right, let's do something like this: the integral of natural log of x over x cubed. So whenever you see something like this, again, I see a mixture. When I see a mixture, I think, could I do a u sub? Here, the answer is no. So I let u equal the natural log of x. The derivative is 1/x. And then I still have x's left over. Now, I will point out, you could do this if you really wanted to. If you wanted to make your life hard, you could do a u sub first. Let me show you what I mean. Don't write this down. I don't think you want to do this. So if we try letting u equal the natural log of x, your derivative would be 1/x dx. Or you could even say dx is x times du. So I could try to really force this. I could say, well, this is going to be the natural log of x over x cubed times x du. One of the x's cancels. So I'm left with the integral of the natural log of x over x squared du. The natural log of x is my u. And then x squared, well, I could do a back sub. I could say e to the u is equal to e to the natural log of x, which is x. So x squared is really e to the u squared, which is just e to the 2u. And so if I really, really, really wanted to make life hard for myself, I could write this as the integral of u times e to the negative 2u du, and then do integration by parts. Or if you find yourself doing a wacky u substitution and getting to a place where you're doing integration by parts, probably means you could have started with integration by parts in the first place. But it's not always true. Sometimes you actually do have to do a u substitution before you get to the more terrible integration by parts part. But here, it's not the case. Here, we would instead let u equal what if we're doing integration by parts here? Do I want u to be natural log of x, or do I want u to be the 1/x cubed part? Good question. That is the thing that people often think, but let's point out. So if we let u equal 1/x cubed, then our dv has to be, what are the words I always say? 2 words. The rest. Right? Once you picked u and you're doing integration by parts, once you pick u, dv is the rest. Always. You have no other choice. You have no choice. dv is everything else. So if u is 1/x cubed, dv has to be natural log of x times dx. And here's the part where people often convince themselves with the wrong thing. Derivative here, not too terrible, right? This is u equal to x to the negative third. du would be negative 3x to the negative fourth. The antiderivative of the natural log of x. I know someone wants to say 1/x, but that's the derivative of the natural log of x. The antiderivative of x didn't class last time. The antiderivative of the natural log of x here is x natural log of x minus x. Not that you're expected to memorize that. But the point here is that we have made the wrong choices in a number of ways. One, our du kind of got more complicated, right? Our power got further away from 0 than closer to 0. And our v definitely got more complicated, right? The antiderivative of the natural log of x became more complicated. We are trying to make things less complicated. So here, and actually almost always, when you're doing integration by parts, if you can let u equal the natural log of x, or actually any log, but usually it's natural log, that is always the right choice. Because we're always looking at, for integration by parts, we're going to choose I feel like someone can make a good integration by parts Valentine's, or like you choose choose you to be the following. Logarithms if you got them, a power of x if you don't have a logarithm, a trig thing if you don't have a log or a power of x. This is the order we choose you in. LATE. So here, if you see a logarithm, you're always picking that first because it's the first letter. So always pick u to be the natural log of x if you're doing integration by parts, if you have a natural log of x. And then what's dv going to be? What's dv going to be? Thank you, the rest. Yes, the rest. dv is going to be the rest, which in this case is 1 over x cubed dx, or I would choose to write it as x to the negative third dx. Let me ask you all one more time. What's dv? Thank you. The rest. It's always the rest. It's always everything that's left. You don't get a choice. And then du is the derivative of that, which is 1 over x, and then multiplied by dx. And v is the antiderivative of x to the negative third, which is x to the negative second divided by negative 2. Then we put it all into our lovely ultraviolet super voodoo formula. uv minus the integral of v du, ultraviolet super voodoo. And so we get that the integral of natural log of x over x cubed is equal to u times v. I really don't, fine, I'll write it that way. Natural log of x times x to the negative second over negative 2. I would probably choose to not exactly write it that way. Minus the integral of v du, x to the negative second over negative 2 times 1 over x dx. Here's where I think people also get jammed up with these natural log ones. When you get to this point right here, that's when you then have to simplify your integrand. Right? We need to make this easier to deal with. And I think I'm going to run out of room, which feels terrible at the end of the page. But oh well. So then this integral, natural log of x over x cubed dx, which is equal to the natural log of x times x to the negative second over negative 2 minus, let's simplify this a little bit. Let's pull out the negative 1/2 to make it a plus 1/2. And then we have the integral of, if we have x to the negative second divided by x, that's really the same as x to the negative second times x to the negative 1, which is really x to the negative third. We're then going to integrate. So not that I would normally write all this, but I'm writing it kind of just to show every single step. X to the negative second times x to the negative first is x to the negative third. And then finally we get to integrate the rest of it and get, let's actually rewrite this as well. I'm going to rewrite this first part as negative natural log of x divided by 2 times x to the positive second. The negative out in front, this 2 still stays in the denominator, but the x to the negative second comes down as x to the second. Plus 1/2 antiderivative of x to the negative third is x to the negative 2 divided by negative 2. And then I do need a plus c here because it is an indefinite. And yeah, I could simplify this more, but I don't really want to. You could rewrite that as negative natural log of x over 2x squared minus 1 on top over 4 times x squared on the bottom plus c. That's probably the better way of writing it. Lots of things come up with integration by parts, right? There's lots of different kind of, yeah, there's lots of things. That's not the best sentence I've ever said in my life, but. That doesn't work out so well. Okay. Let's look at another example. Where'd you go? Other example that I had in mind. Oh yeah. Yeah, that was kind of funky. But we should do it. Where did you go, example? I had it right here. Oh, there you go. Questions. Yeah, let's do that one first. Okay, here's kind of a funky one. The integral of cosine of the natural log of x dx. It's terrible. Go away. Okay. sometimes you get approached by an integral that looks kind of weird, and you don't really have a good idea of what to do. That's a lot. I mean, most integrals, you kind of start off with like, what do I do? I don't know. You just start throwing things at it and see what sticks. This certainly doesn't look like an integration by parts problem because I don't have any multiplication. So typically integration by parts comes from having one other function multiplied by another function. I don't have that here. I have a composition. I have cosine of natural log of x. So unlike the previous problem where we kind of tried to force something, here we are going to kind of have to do a u sub and then maybe have a back substitution. And I'm going to do something, what's the word I'm looking for? I'm going to do something kind of annoying in that I know what's going to happen already. And I also know that I would really prefer not to use the letter U if I'm going to have to do integration by parts after this. So here's what I'm going to do. And I'm going to do a U sub, but I'm going to choose the letter T. I'm going to let T equal the natural log of x. I'm doing a quote unquote U sub, but we're using the letter T. Because we have the foresight of knowing we might end up doing integration by parts next. And we really, for whatever reason, we find it impossible to use letters other than U and V when we're doing integration by parts. Some people use W, but it feels weird if you're using U and W. So I would just do it this way. So T equal to natural log of x, and then our dt is 1 over x dx. I don't have a 1 over x dx. I know it's been a little while, but the thing we do when we don't really have this, but we still want to force the u sub to work, is we take our u substitution, we solve for x, and then we differentiate both sides of that. So the derivative of e to the t is e to the t times dt. The derivative of x is 1 times dx. So then we can rewrite this integral. Oh, I picked something. Oh, I picked something extra gnarly here. That was. Ugh. We might have to come back to this. We'll come back and finish this one, but we need to do something else before we finish this one. Not that we couldn't do this one, but I want to make life not suck quite so much for you all. So yeah, let's pause for a second here and explore one other thing here. Yeah, sorry about that. I forgot this one got super gnarly. This one really get that bad? Yeah, it really does. What wackiness did I do here? Oh. Sorry, oh, that's interesting. You never would have thought to do it that way. So let's actually not switch gears here. Let's talk about how James is making maybe the wrong choice. Because it's good to see this. So here's what I was going to do. And this actually isn't the wrong way, it's just the way I would have thought to do it. So continuing on with this for a minute here, if I actually start rewriting this, this is going to be equal to the cosine of t. And then my dx is e to the t dt. And there is a way of doing an integral like this, but it's in which we are going to do in a minute here. But it's good to see that there are other ways to do things. So I would have done it this way, and then this here, I'll tell you, which we're not going to do it this way. This requires integration by parts twice. 2 times. And then some trickery. But there's not always just one way to do something. So let's look at another option here. Let's try something else. So instead, oh yeah. I often forget about this tactic. You can always try integration by parts if you consider dv to just be the dx. What I mean here is that I can let u essentially be everything cosine of the natural log of x, and dv gets to be just the sliver that is left, which is dx. The rest isn't very much this time. And then we go through our usual, there's a word I'm looking for that I can't find, but well. Derivative cosine of natural log of x, you have to use the chain rule. Derivative cosine of some stuff is negative sine of your stuff times the derivative of your stuff. So negative sine of the natural log of x times 1 over x. I think motions. We go through the usual motions, I think was what I was trying to say. And then the antiderivative dv here, v is going to be 1 times x. So let's see what happens when we throw this formula at it. This is going to equal u times v, so x times cosine of the natural log of x. Be careful, right? That's not cosine times natural log of x, it's cosine of natural log of x, minus the integral of v times du, which is negative sine of the natural log of x times 1 over x dx. Don't forget the dx there. We're going to simplify. Specifically, the x times 1 over x cancels out, and the minus minus becomes a plus. So I'm going to rewrite this as x times cosine of the natural log of x minus a minus is plus the integral of sine of natural log of x. And then we're going to do the same kind of thing. So this isn't really any better than what I was trying to avoid. It's just different. So now we're going to do another integration by parts, but we're going to let u equal sine of the natural log of x. dv is going to be dx. du is the derivative of that, which is cosine of your stuff times the derivative of your stuff. So cosine of the natural log of x times 1 over x dx. And our v is once again x. Okay. So let's watch what happens here. So, and I'm going to write this out purposely. Normally I would just kind of write equals, 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 but I'm actually going to write that my original integral of cosine of the natural log of x, yeah, this pen's definitely starting to go here, is equal to x times cosine of natural log of x plus the integral of sine of natural log of x, which is going to be the uv minus the integral of v du for these u's and v's over here. So it's going to be x times sine of natural log of x minus the integral of x times cosine of natural log of x times 1 over x dx. Well, yeah, let's just observe here that for my v times du, the x times 1 over x will cancel out, and I'm going to get cosine of natural log of x dx. Oh, look, I'm back where I started. I'm back to the integral of cosine of natural log of x dx, which is the integral I started off with, which feels like you might have done nothing, but that's not true. We have done something. So now here's kind of the trickery that occurs in this kind of problem. We're going to take this integral and we're going to add it to both sides. That's why I wrote the left-hand side, by the way, so that we could add it to both sides seamlessly. If I take the integral of cosine of natural log of x plus the integral of cosine of natural log of x, I end up getting 2 times the integral of cosine of natural log of x equal to x cosine of natural log of x plus x sine of natural log of x. Then if I want to isolate the integral over here, I just multiply both sides by 1/2. So the integral I was trying to find, cosine of natural log of x dx, is equal to 1/2 times all of that. Plus c. It almost feels like cheating. Or to me, it feels like you didn't actually do the integral, right? Like, yeah, I didn't actually finish the process, it kind of feels like, but we did. This is actually the antiderivative. And if you wanted to, I don't think we should, if you wanted to, you could check. You could take the derivative of both of all this, simplify, some things would cancel, and once you were done with the whole thing, you would get just cosine of natural log of x, which is kind of cool. This process, this is kind of a unique problem. This is not the usual version I would say that most of you will see, but I want to kind of give you a different one to start off with. Let's look at the more kind of standard version of this integration by parts problem. And then we'll, stop this and trig stuff. Okay. So here's a more typical problem you might see. Let's do the integral of, well, that was cosine, let's do sine. Let's say we want to do the, let's, sorry, keep grabbing the wrong pens here. Let's try the integral of e to the, let's do, sure, e to the negative 3x, yeah, times sine of, let's not get too crazy here, James, just sine of x. These problems get more challenging when you have more, so if you have like a coefficient on x here and a coefficient on x here, the fractions get kind of gross. But if you ever have an e to the x times sine of x, or an e to the x times cosine of x, or an e to the multiple of x times sine of a multiple of x, right? When I say x, you should really hear anything times x. 5x, 7x, negative 2x. Constant multiples matter, but they don't really matter as far as how complex things are. They don't change the complexity. They just make the calculations more terrible to deal with. Whenever you have something like this, or something like e to the 5x times cosine of 2x, for example, this process applies, where we're going to do integration by parts twice. We're going to end up with the same integral we started with. We're going to bring it over to the other side, divide by whatever constant we need to divide by, and then that'll be the answer. So typically, I would choose to make u the trig thing, because again, of this acronym. I don't have a log, I don't have a power of my variable x, but I do have a trig function. So that would be my choice for u. I will also point out that technically here, you couldn't go either way. You could pick u to be the trig thing and dv to be the e to the x thing, or vice versa. You could pick u to be the e to the x thing and dv to be the trig thing. Either way is technically fine. You might, the reason I mentioned this is because you might see people do it the other way. Whichever way you choose to do it, the first time, you have to make the same choice the second time. I'm going to pick to do the way I usually do, which is let u equal the trig thing. dv is going to be what? Thank you so much. The rest. E to the negative 3x dx. And then my du is cosine of x dx. V is the antiderivative of e to the negative 3x, which is e to the negative 3x divided by negative 3. All right, let's throw it into the formula. So this is going to equal u times v. So no, when I see u times v here, I really don't want to write like sine of x times e to the negative 3x over negative 3. I would rather write something like negative 1/3 times e to the negative 3x times sine of x. Just making it so I don't have something times a negative thing, I just put the negative out in front. And we usually like to put constants out in front as well. Minus the integral of v times du. So I'm going to write that as negative 1/3 e to the negative 3x times cosine of x dx. Okay, I'm not going to rewrite it, but I am going to think of it as really a, let's move this out in front and call it a plus 1/3 times the integral of just this. I don't need to include the negative 1/3 in my uv situation. So when I rewrite this, I know I haven't done my udv yet. Just hold on for a second. I'm going to get negative 1/3 e to the negative 3x times sine of x plus 1/3 times whatever my uv minus the integral of v du is going to be. So now let's go back and make our choices here. So I don't really have any choices now. Like before, right? I said excuse me, gosh, you pick u and then dv is the rest. Here, because we're doing this special kind of process, u is already chosen for us already. We chose u to be the trig thing last time. We have to choose u to be the trig thing this time. If you make the opposite choice, what you'll end up doing is undoing the work you've done and getting that the integral of e to the negative 3x times sine of x is equal to the integral of e to the negative 3x times sine of x, which is true and not helpful. If you say something is equal to itself, well, great, yeah, but I didn't get anywhere. So my u is cosine of x. My dv is e to the negative 3x dx. My du is negative sine of x dx. And v is again e to the negative 3x divided by negative 3. So then all that goes into our ultraviolet super voodoo. and we get -1/3 times e to the -3x times cosine of x. There's my u times v minus the integral of v times du. So it's going to be -1/3 e to the -3x times negative sine of x dx. Let's zoom in a little bit there. People might want to see that a little bit better. There, hopefully you can see that a little bit better now. Move this stupid picture of me. All right. I would encourage you all to try and do these problems without writing all the things every time. I'm going to write all the things, but I feel like you could do less writing than I'm about to do. But I'm going to write my original integral. Sometimes people do a thing where they're like, call this I. And then they write I equals this plus this minus some coefficient of I instead of writing the integral. But that's not me. So e to the -3x times sine of x dx is equal to, let's see what we've got here. -1/3 e to the -3x times sine of x. Oh, sorry, you can't quite see all of that. Apologies. And then 1/3 times -1/3 is -1/9 e to the -3x times cosine of x. And then finally, now be careful here. I have a 1/3 times a positive, negative. So it's negative, negative, negative. So I have a 1/3 times 1/3. So it's going to be a negative, 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 negative 1/9 integral of e to the -3x times sine of x dx. And then what we're going to do is we're going to add that to both sides because we've essentially got the same integral we started with. So I'm going to add 1/9 times the integral of e to the -3x times sine of x dx to both sides. Okay, I'm going to zoom back out a little bit. Right there. So now, and here's the people I feel like, for some reason, this last part throws people off. What's this integral plus 1/9 of this integral? Or a better question is, how much of this integral do I now have? If I have a whole integral plus 1/9 of this integral. How many ninths do I have? 10/9, right? 9/9 of this integral plus 1/9 of this integral is going to be 10/9 of this integral. And really, I would almost want to skip the writing the 10/9 of your integral. This is probably where I feel like you could totally skip a step. 10/9 of your integral is equal to all this. -1/3 e to the -3x sine of x minus 1/9 e to the -3x cosine of x. And then finally, multiply both sides, but don't divide by 10/9, multiply by 9/10. Multiply both sides by 9/10, and you end up getting the integral of e to the -3x times sine of x dx is equal to 9/10 times all of that. -1/3 e to the -3x sine of x minus 1/9 e to the -3x cosine of x plus c. So if you see an integral that's e to the 2x times sine of something, or e to the 5x times cosine of something, or e to a multiple of x times sine or cosine of a multiple of x, this is the process. You do integration by parts twice, making the same types of choices each time. And then after you do that, the integral you started with will pop back up at the end, and then you add it over to both sides, and then you multiply by whatever coefficient you need to isolate it. It's kind of a lengthy process. It can be easy for the numbers to get a little bit messed up if you're not super careful. Cool. So integration by parts, there's lots of integration by parts stuff. It kind of just doesn't go away. Where's the other thing I want to say here? Yeah, let's go ahead and look over here. Oh, yeah, there was. Okay, I got one more. Sorry, I know it sounded like I was wrapping up. Someone over the weekend was asking me about this particular integration by parts question that is from the textbook, which is kind of an anomaly, I would say. So let's look at one more, not that it's the last one ever, but just another integration by parts example. Let's look at this. I think this is number 28 from section 6.2. It's the integral of x cubed e to the x squared over x squared plus 1 squared dx. Normally, I don't know. This is not a normal situation. Normally, I don't know what I would do here, right? Like, I don't have a good intuition as to what I would let u and dv be. Fortunately, I think someone tells me what I'm supposed to be. Yeah, that's funky. So here we're gonna pick u equal to x squared times e to the x squared. Why? Because someone told us to. And sometimes that's how problems go. Sometimes someone's like, try this thing. And our dv, what's our dv going to be? The rest. What is the rest? Well, certainly the denominator, x squared plus 1 squared. Is there any of the numerator that I didn't capture? Yeah, an x to the 1. Yeesh. This is going to be gnarly. Because our du, we have to use the product rule for. Derivative of x squared e to the x squared is 2x e to the x squared plus x squared times the derivative of e to the x squared is e to the x squared times 2x dx. I might want to simplify that. And then my dv, I actually have to do the antiderivative of this, which is not like a straightforward antiderivative. So let's see here. My v is going to be the integral of x over x squared plus 1 squared dx. I think I have to do a u sub here for this dv part. Ugh. So pen all over my hand here. I would let u equal x squared plus 1. My du would be 2x dx. My 1/2 du is x dx. This integral is going to become the integral of 1/2 du over u squared. Or if you prefer, 1/2 the integral of u to the negative second. So that's going to be 1/2 u to the negative 1 over negative 1, which is going to end up being negative 1 over 2 times x squared plus 1. Okay, that's my v. So my v is negative 1 over 2 times x squared plus 1. Interesting. Is that really right? Yeah, that seems right. I would like to check it. Here, I'm going to check real quick. If I take the derivative of negative 1/2 x squared plus 1 to the negative 1, it's going to be positive 1/2 x squared plus 1 to the negative 2 times the derivative of that, which is 2x. The 2's cancel. Yeah, you get x over x squared plus 1 squared. Good with that. Okay, check. Sometimes it's good to check. I mean, it's usually not bad, but sometimes it's more feel. Okay, something else to observe here is in my du, I could factor out an e to the x squared and a 2x. If I do that, I'm left with a 1 here and an x squared here. Oh, that's looking promising. So now, writing this out, I'm going to get u times v. So negative x squared e to the x squared over 2 times x squared plus 1. Instead of writing it as x squared e to the x squared times negative 1 over 2 times x squared plus 1. Minus the integral of v, which is negative 1 over 2 times x squared plus 1, times my u. Oh, my u. That's v. Oh, no. What's the formula? uv minus the integral of v times voodoo, v du. Okay. So 2x e to the x squared times 1 plus x squared, or x squared plus 1, if you want to write it that way. I forget the dx, James. And then the x squared plus 1 cancel, the 2's cancel. You can rewrite this as negative x squared e to the x squared over 2 times x squared plus 1. Minus a minus is plus. And then we have the integral of x e to the x squared. And then you do a u sub there. Not terrible. It's a terrible problem. The point of this problem isn't so much to do all this, although doing it is not a bad exercise, but to see that sometimes you might have an atypical choice for your u when you're doing integration by parts. And normally, again, there's no normally here, but usually what I would think about doing is picking u equals to a logarithm or a power of x or a trig thing. Here, I don't know. I really don't know what I would have done if I had not been given direction. I would have tried things that didn't work for a while. That's probably what I would have done. This ends up being negative x squared e to the x squared over 2 times x squared plus 1. And the antiderivative of x e to the x squared, I think we have enough experience now to be able to, well, I know that's going to be 1/2 e to the x squared. Because I know that when I take the derivative of e to the x squared, I get e to the x squared times 2x. So then that'll take care of that x right there. If you like, you can think of this as a 1/2 times 2x, and then there's my u, there's my du. All right, let's talk about some trig stuff. People were definitely asking about trig. I know we talked about trig a little while ago, and I was kind of like, oh, maybe I'm doing this a little too soon. So more trig. Yeah, sure. Sometimes, sorry, I'm about to write something down. I'm like, does that really? Sure, let's take a look at this. Let's say I have the integral of cosine of x over. I feel like we're not ready for that. Let's try that. Sine of x plus 1. A lot of times with integrals that are kind of purely trigonometric, meaning you only have trig functions, you don't have a mixture of things. Oftentimes it's going to be a u sub. It's either going to be a u sub or maybe like just some rewriting, trying to make it look like something we can deal with. So here, I'm going to say I might let u equal sine of x plus 1. And my du is exactly cosine of x times dx. So this integral is going to become the integral of du over u. Excuse me. Which is then going to be the natural log of the absolute value of u plus c, which is going to be the natural log of the absolute value of sine of x plus 1. Let's see. Not too terrible to start. I thought I had a good example here. I'm just kidding myself. I know where they are. It's hiding from me in this stack of papers. Well, we could do those. Sure, yeah. All right. So let's look at a few more. Let's say we want to do the integral of, let's do that one. Sine x over cosine squared x dx. There are two equally valid ways of approaching there. So a lot of these trig integrals have a number of ways. One way you could do this, the way that seems sensible to me, is to try a u sub. What's a good choice for you here? In fact, don't say anything. Write down your choice for you. Make a choice for you. I would say you want to keep it simple. You either want to pick u equal to sine or u equal to cosine. Those are your plausible choices here. Once you've chosen, find your du. Keep going. Don't stop. I want to find the problems hiding from you. There you are. Found it. Cool. So the choice we definitely should make here is u equal to cosine of x. It's mostly because the derivative is essentially sine of x. And I definitely have a sine of x times dx. If I picked u equal to sine, my du would be cosine, and I don't have a cosine of x times dx. So here I would make a small adjustment. I would rewrite this as negative du equal to sine of x times dx. And then I would rewrite this as the integral of negative du on top, u squared on the bottom. And then I would rewrite this as negative integral of u to the negative second. And we're going to integrate. Negative, the integral of u to the negative second is u to the negative first divided by negative 1. And then we could definitely rewrite this as positive 1 over u plus c, which then becomes 1 over cosine of x plus c, which is a perfectly fine way to do this, and probably the way I would recommend doing it. But I will also point out that sometimes you can see something, meaning the less intuitive way to see this is to say, oh, I have 1 over cosine times sine over cosine, which I could write as secant times tangent. And we know that the antiderivative of secant times tangent is just secant, because the derivative of secant is secant times tangent. Again, I don't think this is the right way to do this problem. It's not wrong per se, it's just not the, I would never see it this way versus the other way. But I will point out, these answers are the same. 1 over cosine is the same as secant. So either way you see this, and you might see it differently, is a fine way of doing it. Yeah, let's look at a little more interesting problems. Let's say we have, how much time do we have? Not a lot of time. So here's one that comes up often. Often. Let's say I want to find the integral of sine cube x dx. Oh, this problem is tricky. So when you have powers of sine and cosine, the power of sine is odd. There isn't a cosine here, but technically you could say to yourself, well, the power of cosine is technically even. There's a cosine to the 0th power. 0 is an even number. Let's look at a slightly different situation, though. We'll come back to this, I promise. Let's say we had the integral of sine of x times cosine squared of x. There is a better choice. There is a best choice and a terrible choice for you here. So you can pick u equal to either one, actually. But look what happens. If I pick u equal to sine, things are not going to go well. And here's why. The derivative of sine is cosine of x dx. And when I try to rewrite this, this is going to become the integral of sine of x times cosine of x times cosine of x times dx. It's cosine squared, it's cosine times cosine. I'm breaking this up so that we can see that one of these cosines gets soaked up by the du. Sine was our choice for u. And this extra cosine is problematic. What we should have done is made the choice where u was equal to the trig function that's raised to the even power. in this case. So that if we pick u equal to cosine, our derivative is negative sine of x times dx. Negative du is positive sine of x. And so when I write this, I can write this as the integral of cosine squared x times sine of x times dx. And now my sine of x times dx is my negative du. There's no signs left over. And so then we can say cosine squared is u squared. And this becomes the negative integral of u squared du, which is straightforward-ish. So I get negative u cubed over 3 plus c, which is negative cosine cubed x over 3 plus c. The upshot here is that when you have powers of sine and cosine, when you have powers of sine and cosine in the numerator, typically you want to let, if you have an even and an odd one, you want to let u equal the trig function that's raised to the even power. So watch this trickery. We're going to let u equal cosine. I know it feels very strange. You know how we can make it feel less strange? We're going to do the trig identity part before we do the u sub part. So here's the way to make this feel less terrible. We'll come back to you. Promise. Before we do that, we're going to rewrite this integral as sine of x, sine squared of x times sine of x. And then we're going to replace sine squared with its trig identity, which with one of its trig identities, because there's actually two different trig identities for sine squared, and we want to know both of them. So sine squared, I will remind everybody of my favorite trig, well, not my favorite, but one of my favorites, that sine squared x plus cosine squared x equals 1. Which means sine squared of x is equal to 1 minus cosine squared of x. So I can rewrite this as the integral of 1 minus cosine squared x times sine of x. Are we cool with that? Does that seem okay? Now it seems plausible that we could make u equal to cosine. Right? That doesn't seem like such a stretch anymore because there actually is a cosine in there. But it would have been totally fine to have done it from the get-go. It just feels weird. So then we're going to let u equal cosine of x, and our du is negative sine of x dx. Our negative du is positive sine of x dx. My sine of x dx looks pretty terrible there. And then we can rewrite this integral as the integral of, well, the sine of x dx is going to be the negative du. So we're going to write this as 1 minus u squared. Don't just write negative du here. You write it like that, it looks like you have 1 minus u squared minus du. It has to be times negative du. And then I would rewrite this as, here's how I would really rewrite it. I'd write it as u squared minus 1. Minus 1 times 1 is minus 1. Minus 1 times minus u squared is u squared. And I would change the order to have the minus thing second. Or you can just put the minus sign out in front, whatever you want to do. And then we integrate, we get u cubed over 3 minus u plus c. We plug back in that u is equal to cosine. And we get cosine cubed x over 3 minus cosine of x plus c. Kind of funky. And I was going to do another one, but that's time. So